we will see this example. So here they have given entities. We will discuss. The steam boiler furnace is constructed out of a layer of fire clay. Fire clay. This will be the layer of fire clay of 125 feet thick and a layer of red brick. Another layer is of red brick. Suppose this will be second. First, another layer of red brick of width 500 mm. Of width 500 mm. If the wall temperature inside the furnace, that is this temperature, so they given us B1 125 mm will be equals to 0.125 meter. Then B2 as 500 mm, that is equals to 0.5 meters. And T1, suppose consider this surface temperature, that is inner surface temperature, as T1, that will be given as 1373 Kelvin, and outside wall temperature is this temperature, so this will be T2 as 323 degree Kelvin. That determine amount of heat, but they want to know find amount of heat loss per meter square of wall furnace wall area. So they given us area as a 1 meter square. So this will be the first case. Here they want to find Q. They want to find Q. Now, then they said us that if it is desired to reduce the thickness of red brick layer, that is this layer number, so first layer will be as it is, and another second layer width will be, this will be the first layer of width 125 mm, and another layer, that is red brick, is second layer with half by, that is half, means its initial width is 500, now it is 250 mm. By filling a space between two layers by diatom. So here they have filled in this, suppose its width will be P, material 3, filled with diatomite with K variation of K, that is its thermal conductivity, its function of temperature, that will be equals to 0.113 plus 0.00016 T in watt per meter Kelvin. Estimate the thickness of filling to ensure an identical loss of heat. That is, here we have calculated Q. Here Q will be same, then T1 will be same, and T2 will be same. Also, they have given us the K1, that is K for fire fly, as 0.533 watt per meter Kelvin. K2 as 0.70 watt per meter Kelvin for red brick. So we will need to solve this example. Here they have given, we have write all this. So electrically equivalent system to this system has This will be R1, that is resistance to heat flow due to wall number 1, and this will be R2 due to wall number 2, that is red brick wall. They have given us a temperature at this location as T1, and this will be T2. So we can write its equivalent electrical circuit as R equivalent with this temperature at this point as T1, and at this point it is at. So we can calculate the values of resistances. So first we calculate R1, that is resistance due to wall 1, that will be equals to B by KA, that is B1 by K1A, which is equals to 0.125 by K1. K1 is 0.533 into A. A is units of 1. We will get R1 as 0.2345 Kelvin per watt. Similarly, we calculate R2 B2 by A2A, which is equals to 0.5 by 0.7 into 1, which is equals to 0.7142 Kelvin per watt. Now we know for this are series, so equivalent resistance will be equals to sum of the all series resistances. So R1 plus R2, 1 plus R2, that will be equals to 0.2345 plus 0.7142. We will get R equivalent as 0.9488 Kelvin per watt. Kelvin per watt. Okay. Once we get R equivalent, then we know Q is equals to delta T on R equivalent. So here delta T is T1 minus T2. T1 minus T2 on R equivalent, it is equals to 1373 minus 323 upon 0.9488. We will get value of Q as 1106.68 watt per meter square. So heat loss, we will get heat loss as 1106.68 watt per meter square. So first case is completed. We will discuss case number 2. In case number 2, they tell us that the second wall, that is red brick, as a thickness will be reduced to half of initial, that is initially it is 500 by 2, so it will be 250 mm, that is 0.25 meter. Similarly, R1, that is resistance 1, we have calculated initially, and its value will be 0.2345 Kelvin per watt. Okay. So now this its equivalent electrical circuit, will be, this will be R1, this will be R2 dash, as here width is changing, so R2 will change, so we write R2 dash, and this will be R3 resistance. Similarly, they have given us temperature T1 of 1373 Kelvin and T2 as 323. Now here suppose consider temperature as T3 and here temperature as T4. So we know they tell us that Q will remain same as that of initial. So they given us Q is equals to 1106.68 watt per meter square. Here we consider area as 1 meter square, so it is in watt. Okay. So we can write Q will be equals to T1 minus T2 upon R equivalent, that will be equals to T1 minus T3 upon T1 minus T3 upon R1. Also we can write this as T4 minus T2 4 minus T2 divided by 2 dash. So first we know value of R1, value of Q. We will take Q as 1106.68 will be equals to T1. Value of T1 is 1373 minus T3. We don't know the value of T3, divided by R1. R1 is resistance 1, that will be 0.2345. Once we calculate this, we will get T3 as T3 1113 and 113, that is 1130.7 degree Kelvin. 113 1113.7 degree Kelvin. Similarly, we will calculate resistance 2 dash, that is resistance change with change in width. So it will be B by KA. It will be equals to B. Here B is 0.25 divided by K. K is 0.7 into A. We have considered unit area, so it is 1. So we will get R2 dash will be equals to 0.3571 Kelvin per watt. That is 3571 Kelvin per watt. Once we get R2, then we can R2 dash, then we can take, we will take this will be equals to this Q, that is 1106.68 will be equals to T4. We don't know the value of T4 minus T2. Value of T2 is 323 divided by R2 dash, that is 0.3571. Once we calculate this, T4 we will get as a 718.24 degree Kelvin. So we will get T3 as well as T4. T as well as T4. T3 as well as T4. Once we get T4, then we know for this middle plate, Step number 3, which is inserted in between, and we want to know its thickness. That middle plate is of diatomite. Diatomite. We don't know its thickness. Will be B. We get the surface temperature at this location, that is T3, and at this surface temperature will be T4. Now we will consider this as a single object with X, that is heat flowing in this direction. They have given us Q also. Also we know T3, T4. So and they tell us that K is a function of temperature. K is a function of temperature. That will be equals to K as a function of temperature, and that will be equals to 0.113 plus 0.00016 T. 0.00016 T. So what we will do according to the Fourier's law? According to Fourier's law, Q is equals to minus K dt by dx. Here we know area, its value is 1 meter square. We have considered it is unit area. So we can write Q is equals to minus K into dt by dx. So we are taking this denominator on right hand side. We will get Q into dx will be equals to minus of K into dt by dx. We know K is a constant, and its value also we know. So and K as a function of temperature. Sorry, this we have shifted to left hand side. So we can write boundary conditions. Boundary conditions at x equals to 0, that is on the surface temperature T3 will be equals to 1103, 1113.7 degree Kelvin. At x is equals to B, that is at this surface temperature will be T4, that is 718.24 Kelvin. Now we will integrate this equation. That is Q, integration of Q into dx. X is from 0 to B will be equals to minus of K. That is we are substituting value of K. Integration of K. K is 0.113 plus 0.00016 T into T of T. Here is varies from 1113.7 to 718.24. So integration of x raised to n dx will be equals to x raised to n plus 1 divided by n plus 1. This is the standard formula. Here we can write dx as x raised to 0 into dx. X raised to 0 is always 1. So x raised to 0 dx will be equals to Yet substitute value of n as a 0, then x raised to 0 plus 1 divided by 0 plus 1. So it will comes x upon 1. So this integration will be equals to q into x from 0 to b. 0 to b. This will be the right hand side, sorry, left hand side, and we will solve first this and we will get q into b on left hand side. Now we will integrate, we will integrate right hand side. So right hand side is minus of integration 1113.7 to 718.24 from 0.113 plus 0.00016 t into dt. So first we multiply this dt to both, and also integration we can write this integration as minus of integration 1113.7 to 718.24 0.113 t of t plus 0.0016 t into dt from 1113.7 to 718.24. This dt we will get t. Once we solve this integration, we will get q into b will be equals to 102.58. Now substituting this value of q, that is 1106.68 into b will be equals to 102.58. Here unknown is b only. So we get b as 92.69 mm. 92.69 mm. That is, b will be equals to, in terms of meter, 0.09269 meter. That is 92.69 mm.